Okay, so this is the instruction for lab, what I call the solar rotation. And you're going to use the image of the sunspot as taken by the mission SOHO as a way to measure the solar rotation. So let's just look at image number 1, June 22nd, and I believe, like I said, it's 2002. So let's look at just different set of sunspot. In this set, you're going to see A, B, C, D. I mean, we could use other set, but this is good enough. Let's look at set A, and let's look at later on. You will see, for example, set B coming out. So let's look at June 22nd, the first day of this image. And you're going to record latitude and longitude. Okay, remember, this is minus 60, minus 45, minus 35. This is your longitude. Okay, this is what you call the longitude. This is the longitude that we lay on the surface of the sun, just like the longitude on our Earth's surface, okay? And this is latitude, 15, 30, 45, 60, okay? So let's look at A. Let's look at A. What is its longitude and latitude? What is the location of the sunspot A on June 22nd? So it is minus 15, right? It is minus 15 because the latitude is here. Oh, by the way, it depends on how you do longitude, latitude, longitude. Okay, I tend to do latitude first, but let's do longitude. The longitude right now, think about this. This is 0. This is minus 15. This is minus 30. This is minus 45. So this is minus 60. So what is the longitude of A? Well, it's probably around minus 59, right? It's close to minus 60, but it's before that. So it's not minus 60. Around minus 59. I mean, 59, 58. Is it enough? Does that make sense to you? This is how you're going to read the position of these sunspots. Okay? So let me just look at the next day. So we are observing these sunspots day by day. The sunspot lives on the surface typically from days to weeks. They're not very long. So once you see the sunspot, you have to observe them on a daily basis until it disappears. And so the next day, June 23rd, you see A has moved to this spot right here. So its latitude is minus 15, and its longitude, this one is easy, is minus 45. This is a minus 45 line. Okay? Let's look at June 24th. So A has again moved this way now to the right. So again, it's on latitude of minus 15. And what about longitude? Now you have to make an estimate. Remember, this is minus 30. This is minus 45. So this position right here, okay, this position is right here. You can make an estimate and say it is about, maybe minus 32 or 33 right here. Make an estimate, right? Because this is 30 minus 30, this is minus 45, and so on. And so just for an exercise, make sure you understand. What about the position of C, sunspot C on June 24th? How would you measure this? This would be, this is latitude 15, this is latitude 30. So the latitude here, let's make an estimate. Okay, it looks to me like it's about 18 or 19, maybe 18. Okay, about 18 right here, because 15 is right here and 30 is right here. So the latitude is about 18. What about the longitude? The longitude, you have to estimate up between 30 and minus 45. Again, it looks to me like it's close to about, not quite 1/3. So it won't be minus 35. Okay, so it might be minus 34, 33. Okay, say minus 34. So you have to make that estimate. Do you understand? So you can do this with A, B, C, and D. Now, a lot of people ask you, oh, look at D. D is an extended object. Which one do I use? Well, it doesn't matter. You can use this guy right here, the dark spot, or you can use this one. Okay, for as long as you're being consistent. So let's go to the next one. This is June 24th. Right, now D has moved from 23rd, right? It was right here, just passed beyond longitude of 30 to now passing beyond the longitude of 45. So if you look at that dark spot, it's about 46 right here. So just, this is an extended object, but let's just pick one. You can pick here or there, but just keep it consistent. Whichever you pick, just use that, okay? A is easy because it's one big giant, magnetic field. B is easy, C is easy. But when you look at D, you have to pick which one is it that you want. Is it this one? Is it this one? Or is it this one? Of course, I recommend the obvious one, the largest one. Okay? And so you're going to do this for all the sunspots over time, okay? All the way to July 3rd. Okay? So June 22nd to July 3rd. So around 10 days. 10 days of sunspot motion that you can absolutely see. So even from this images, this set of images, you can see that the surface of the sun rotates. Okay? And so this lab, what you could do is you're going to put the date here, and you're going to put longitude, just longitude, not latitude here. Okay, just the longitude, because the motion of the sun is rotating, right? So it's moving from left to right. So that's longitude, right? And so what you're going to measure is longitude. Remember, you might not be able to record every date. So when you don't have it, you don't need to record it. Okay? And so label your sunspot A, B, C, D here. Put your latitude here. Normally, you're not going to use the latitude at all. But roughly, what latitude is for its 10-day duration, just an estimate. But the initial date and the final date, the initial longitude, final longitude for each sunspot. And then we're going to do an easy way. For this lab, I'm going to make it easier for you. Just take the initial day and the final day, and take the final minus initial, right? Final longitude divided by, minus the initial longitude divided by the number of days, okay? Now remember something that's very tricky. I think some of you will make this mistake. Let's say, make sure you understand. Let's say A moved from minus 60. Let's just make it simple. A moved from minus 60 on June 22nd to here on the 10th to here to 30. So what is the longitude that it has moved through? Right? Remember, it goes from minus 60 to 30. So what do? You do 30 minus 60, which would be 90. Okay, so make sure you understand the minus sign here. But of course, if you just look at it, just use your common sense, you will see, oh, this is 30. And this is 60 right here. And this is 30. Of course, when you add up this way, when you look at it geometrically, then obviously it's 90, okay? And so if you're not sure, visualize and make sure your algebra is correct. What about days? What about days? This is a little bit tricky. If I tell you, if you observe from day 1 to day 3, day 1, day 2, day 3, how many days have you observed? Day 1, day 2, day 3. How many days? The answer is 2. Okay, when you go from day 1 to day 2, that's 1 day. When you go from day 2 to day 3, it's 2 days. All right? And so when you go from day 1 to day 10, how many days there? 9. Okay, so I know some people just divide by 10 and you get it wrong. So, science is a little bit tricky. Sometimes mathematics is a little tricky in that sense. So you have to think about actually how many days has elapsed from day 1 to the final day. So make sure you understand when you do degrees by day, the degrees you must get the positive sign, minus sign correct. And the days you must get the interval of the number of day intervals correctly, okay? So that's two tricky part. Both are a little bit tricky for someone. Every semester, some students will get confused about either of the degrees or day, for both, right? Now remember I explained to you about the longitudinal motion, about the synodic period. Well, this is where you need to just plus 1. I don't need to go through that again, but because Earth is moving 1 degree per day, and so in order to compensate for that, without long explanation again, you just need to plus 1 to it. So we'll take whatever the longitudinal motion, which is like the velocity, degrees per day, just plus 1. Just add 1 to it. That's it. Brainless. All right? Now, how do you figure a rotational period? All right? What you do is you take whatever this number is. Let's say this number right here is 10 degrees per day. So use logic. If I tell you the rotation is 10 degrees per day, 10 degrees per day, then how many days would it compare what it takes to complete one complete rotation, which is 360 degrees? If the motion is 10 degrees per day, then how many days would it take to complete the entire rotation, 360 degrees? Well, it takes
36.
36 days, exactly. All right, so you can even use your logic to figure it out. But the way you do it is you take 360 degrees, the instructions right here, and divide it by this number, okay? Suppose you have 10 right here, then you take 363 divided by 10, then you have 36. So that is the instruction, all right? And so since it's just being recorded, and I think that's enough instruction for you, so make sure you understand what I mean by record day, record your longitude, pay attention to plus sign, minus sign, and then when you do algebra, look at the picture to see what makes sense. And when you do the day, make sure you're counting the actual number of days, not just what you're labeling. Make sure you add 1 to it to compensate for the motion of the Earth's orbit, which is 1 degree per day. You just add 1 to it, even if you don't understand it, just add 1 to it. And then the period of rotation is whatever this number right here, which should be anywhere from 5 to 30, okay? It should not be too high of a number, somewhere around 10, maybe 5, maybe 10, maybe 20. And take 360 degrees and divide it by the number, okay? And that should be the period of rotation of the sun. So imagine that in the simple lab, by observing the sunspot, you can actually figure out what is the sun doing in terms of rotation, okay? And this is what this lab is about.